We are here in our last section in Psych 207 data analysis, and it's this area, and thankfully it's pretty short, in what we call non-parametric tests. So everything so far that we've done has dealt with the normal curve when we're looking at our statistical tests. And the normal curve involves continuous variables. But what if I wanted to measure something like frequencies, where the differences, say, in the number of times I get a badminton bird over the badminton net? That's a counting aspect, that's a frequency. It doesn't really fall into the normal curve. So what are some examples of what we call non-parametric tests that we can use? And the same thing can be said for what if I'm using a continuous variable and the distribution is skewed, right? We saw before that with t-tests and with ANOVA, there was this assumption of the homogeneity of the variances. But what if the variance is skewed to one way or the other, or the distribution is skewed? What then? So this is where non-parametric tests fall in. And so there's always some options when we violate these assumptions, or if we're using measures that are not of a continuous nature. Our section in Chapter 17 here then is going to be pretty much a brief overview of these types of tests, and just so that you're aware of them. You're not going to run them. There's not going to be anything on SPSS, although you can run these on SPSS. You're not going to have to do them or anything. But you should be aware of what we call non-parametric statistics. So the term non-parametric refers to the fact that these tests, again, don't require the same assumptions that we do about population parameters. And neither do they test hypotheses about population parameters, right? So this is why they're called non-parametric, not really related to the population. Okay, so in previous examples, as we said before, t-tests and ANOVA, those are called parametric tests because they depend upon, in part, the normality, right, or the distribution of the data being normal, right? With non-parametric tests, that distribution sometimes is not normal. It might be skewed one way or the other. And the other side of it, too, has to do with sample size, as we'll see in the next slide coming up. A couple of things with the assumptions that we've been making the entire time with parametric tests up to now. The first one is that the variances of each group are similar. We saw that with t-tests where we had to run, and also in one-way analysis of variance, where we had to run Levene's test to assess whether or not the variances were the same. If the variances weren't the same across the groups, then we had to use those adjustments that we saw, running t-tests and running analysis of variance. So that's the first one. The second one with parametric tests is that the sample size is actually large enough to represent the population. Now, we saw that in the influences of how sample size might have on the standard error, for example. And I think sometimes there's rules of thumbs where a sample size of 30 might be enough, but you run into problems. It's actually more complicated than that. So we have these rules of thumbs that will say, well, if you have a sample size of 30, you're pretty close. That's not always the case. Because in some cases, you might have a sample size of 30 and the distribution might be skewed in one way, right? So this is what we mean by non-parametric tests. We kind of get around the assumptions that we normally hold with parametric tests. Non-parametric tests don't require the same assumptions. So, for example, I could have a distribution of a sample that is skewed one way or the other. If that happens, then it's time to use a non-parametric test because we violate that principle of normality, right? The second one is that sometimes with parametric tests, we use frequencies, that is to say counting factors. Well, if I'm looking whether something occurs or not, it's really hard to put that on a normal curve. A normal curve is a smear of scores. Frequencies are kind of harder edges. It either occurred or it didn't, and I'm going to count up the number of occurrences versus the number of ones that didn't occur and convert those into percentages or proportions. So that assumption also we don't have to hold. It's not going to be on a similar normal scale as we would see with a continuous variable. Let's take a look at a different one here, and this is what we call a chi-square test. A chi-square test is a type of non-parametric statistic, and those of you in the medical fields will see chi-square tests. Psychology might see them as well. So they do pop up from time to time. And in this case here, what a chi-square test is is the unit of analysis that we're measuring, or measures, are not in continuous variables, or they're not ordinal variables, but rather they are frequencies, right? Or the number of cases that might pop up in specific independent categories. And so these are, if you want to think about it this way, these are counting ones. I count how many times a certain event is going to happen. And so how chi-square works very simply is it compares what we think is going to happen. These are what we call the expected results, and there's a way mathematically to set that up. And we compare that to the actual observed results. And so if the observed results are far away from or are very different from the expected results, then we say that there's a significant difference there. And this is how we determine whether or not the expected frequency really is different from what the observed actually is. And again, just to reiterate here, that the difference between, specifically with the chi-square test, is the nature of the data. And again, with a ANOVA and t-test, the data are continuous. Chi-square, the data again are frequencies. How frequent does a score occur? Just to expand the previous slide a little bit, what I meant by expected frequencies, that's the number or the distribution of frequencies that you would expect to occur by chance. And so it still goes back to what we've always been doing. Did these frequencies in these groups simply happen by chance, or are they a result of the independent variable itself, or that particular category? And so what we're going to do now is we're going to go over an example of what we call a one-sample chi-square. There's other different types. We'll look at the first one, and this is also called the goodness of fit test. And this will kind of give you a sense of how chi-squares work. In essence, a chi-square works, like I said before, by counting up the number of cases or occurrences or frequencies in specific categories, right? And then as we're going to see on the next slide, what the comparison is it takes a look at the proportionality. We convert those frequencies into percentages or proportions. And then those proportions that we see in what we call the observed frequencies are compared to what we would think would happen with what we call expected frequencies. And those are the ones that might happen by chance. And then we begin to take a look and see if there's a large enough difference between the observed and the expected proportions to see if there's a significant difference. And that's where the null hypothesis shows up, right? The null hypothesis specifies the proportion of the population that should be in each of these specific categories, or in each one of these specific independent, or the levels of the independent variable, right? That's the expectation. Okay, and so again, we compare the proportionality of what should be with the null hypothesis to that which we actually observed. We see this here when we take a look at the research hypotheses and the null hypotheses. And the pattern is very similar to what we've been doing before with one-way analysis of variance, except that what we don't see are means, right? Instead, we see the capital P here, and P stands for proportion or percent. So the null hypothesis states here that if I've got three different categories, there's going to be a certain number of proportions in each one that are going to be equal with one another. The research hypothesis is going to come out and say, no, we think there's actually going to be a difference in the proportions across each one of the categories. And so if there is actually, if the difference is larger than the equals, then we can say that there's a significant difference in the pattern of frequencies that we've seen. This is some of the math in behind computing a basic chi-square. Not that you're going to have to do any of this by hand, but just so that you have some, those of you especially going off into graduate school, will have some exposure to this. And really, again, we're looking at different scores here, which is what a lot of what we do in statistics, except in this case here, if you take a look at the top part of the fraction, the numerator, instead of having, the raw score minus the mean score, what we have here is the observed score minus the expected score, that is to say, the number of frequencies, right? And then we simply take that difference, square that, and then divide it by the total number of expected frequencies. Then you have the sigma value, pardon me, on front of the fraction, so you sum up all of those, And this is going to give you what's called your chi-square statistic. And there's certain tables you can compare it to see if your x squared there, or chi-squared on the left-hand side there, if it's large enough, then there's going to be what we call a significant difference that occurs. Now you might be asking, if you're asking, how on earth do we get the expected frequencies? This is actually part of the research hypothesis, right? Now SPSS will run it for you, of course, but the researcher might actually be part of the hypothesis in terms of getting some assessment of what the expected frequency of a variable might be. Now, likely most of this is probably not making sense, or you're bored to tears. Let's look at an example then. Examples can sometimes shed light on the concepts. So this is right from Selkin, page 303, and it's what we call a one-sample chi-square test. And so the research question is, are respondents, and again, here's the sample size, are they equally distributed in terms of proportions for their preference of a food voucher? Now, right away, you can probably work out the expected frequency if they're equal. You've got 3 different groups here. You're for the voucher, maybe you're for the voucher, you're against the voucher, and you've got a sample size of 90. So this is a very simple example. We can actually work out the expected frequencies, because if I divide 3 into 90, I'm going to get 30, which would make sense. If there's equality across the proportions for preference, then the sample size in each one of these, right, for voucher, maybe against, should be a sample size of 30. But we actually see there's a difference here across the different preferences. And so we're going to take a look at this in the slides coming up. So we see here in this slide, down at the bottom, the expected frequency again would be 30. Now this is a very simple one to do, and I use the simple examples to kind of show where the math kind of relates fairly easily. Complicated examples, again, are much more complicated. But we would expect that there would be 30 in each category. And so if they were equally distributed, this is what you would see. You would see the same proportion of responses in each category, right? But now what we have to do is we actually have to go through the math using that previous formula to see what the calculated chi-square statistic is, based upon the differences between the expected frequency 30 and each one in each particular instance here, the for, the maybe, or the against. We're going to take a look at the differences there, sum up the squared differences divided by the expected frequencies, and we'll get our chi-squared statistic. And this is the table that that we would set up if we were doing a very simple chi-square. And again, SPSS will do this for you. On the lower right-hand corner there, I've put the formula again, and so we have our table here. And so, just to kind of explain what the table is, this again are our categories, our 3 independent categories. These are the observed frequencies here, so 23, 17, and 50, right? These are the expected frequencies, 30, 30, and 30. It's again what we would expect. D stands for the difference, right? So the difference between 30 and 23 is going to be 7. Now, it doesn't really matter whether this is a negative or positive. Even if I were to go 23 minus 30, I would have minus 7. It wouldn't matter, because if I take the difference between the two and I square them, I'm always going to get a positive value. So this could be positive 7, it could be negative 7, depends upon which way you want to do the subtraction. It's the same thing for the maybe, same thing for the against. And so what we see here is we see that as the categories move in this particular direction here, for, maybe, against, we see that the differences in between the observed frequencies and the expected frequencies get larger. Notice that down at the bottom that both of the observed and expected are going to be of the same value. So what we do then is we then take the differences like we see in the formula here and we square them. So this is going to be 7 squared is going to be 49, 13 squared is 69, 20 squared is 400. Now we add up all those together, right? And then we simply divide by the number of expected frequencies here, again, which would be 30. So we take 49 divided by 30. This is equal to 1.63. 169 divided by 30 equals 5.63. 400 divided by 30 equals 13.33. We then add all these squared differences, right, divided by the expected up, and we get a value, and that value is on the next slide coming up. When we add up all these values here in the far right column, what we get is we get a chi-squared statistic. I sum up all these, I get a value of 20.6. Now again, there's a chi-squared table that you can take a look at, or SPSS does this for you, that lets you know whether or not your chi-square statistic is significantly different or not. That is to say, whether or not there really are truly differences across all these categories, right? So it's very similar to having a t-statistic with a p-value or a or an f statistic for an ANOVA. You're going to have a value there whether or not it is statistically significant. It's the same thing here, except this is a chi-squared statistic. So this is what you might see in a journal article. If they've done a chi-square, you're going to see this chi-squared value. They give degrees of freedom here as well. Again, depends upon the number of categories, right? So you're going to see chi-squared equals 20.6. In this case here, the p-value is less than 0.05, and so in this case here, the statistic is significantly different, and so you would come to the conclusion by saying, yes, there were significantly different proportions of agreement with respect to attitudes towards food vouchers, right? That would be your statistical conclusion. So it's written out again very similar to what you might see for a t-test, right? Probably the closest example here. But again, the critical statistic here, or the chi-square statistic, may or may not be significantly different. Again, this is where SPSS has in its memory bank tables. It actually does it through a series of calculations, not exactly a table. But there are table of chi-square values as well. Depending upon the degrees of freedom, these two things are linked. They'll let you know whether or not there is a significant difference across the proportions or not. This is just an example of an SPSS output of a simple chi-square test using the exact same data that we just went through. And again, it's very, very easy to interpret in the sense. It gives you, SPSS will give you the observed and expected frequencies here. The residuals really are the differences, right? And you can see in this case here, these are -7, -13. Why? Because you're subtracting the expected from the observed. So I'm subtracting 30 from 23. I'm going to get a value of -7. I had +7 in the other one. Perhaps it should have been minus. It doesn't matter because we square these residuals, or we square these differences together before we divide them they're divided by the expected frequencies. So down here below, you're going to see chi-square. This is going to be the chi-square statistic, and it gives you your sig value here. And in this case here, it's less than 0.05, and so we would say that there's a significant difference somewhere across these three here. Now, the thing is, it doesn't tell you where there's a difference. It simply just tells you that a difference exists. We've just scratched the surface of chi-square. We did a very, very simple, like a 1x3 type of table. There's a bunch of different tables. You can do 2x3, 2x5, 3x5 tables. There's really no end to how many tables you can put together, given that you have enough individuals for each particular cell in that table. So, for example, the third point here with respect to chi-square restrictions, the expected cell frequency for any cell should not be less than 1. So, if you have too large of a table, you can get values that are 0 in 1, and then you have problems with the math and with the interpretation. Right. So there's correction factors that you can use, and again, only if you're using chi-square would you actually go through this. We don't have time in the course to do this. A helpful website, and again, this is again just strictly using SPSS, is layered statistics. If you're going to move on in this course and actually use SPSS for data analysis, I encourage you to get a copy of Andy Field's textbook. You can just put in SPSS in Andy Field and you'll get his textbook. It's very, very robust. It's incredibly detailed. Layered statistics isn't bad. It's you pay for the service with this. It's not a whole lot, but it will give you some examples of using SPSS and statistics calculations.